By welcoming everybody to this our second day in Climate Week here at Penn Engineering. Today we're truly honored to have Associate Dean for Research, Kerry Keegan, to discuss agriculture, energy, and technology, and how technology can help us really combat climate change and global warming. We're very delighted to have you, Professor Keegan. And to lead us off into the program, I'd like to introduce my colleague, Leandra Davis-Kern, who will be our moderator for today's event. Leandra is the Senior Director of Planning, Design, and Construction at Penn Engineering. She's also the leader of the Green Team and has also been very, very instrumental in helping us plan the Climate Week here at Penn Engineering. So Leandra, I'll hand it over to you.
Thank you, Osek. Thank you for joining this intriguing conversation today featuring Dr. Sherry R. Keegan and Penn's new Engineering Research Center. I am honored to introduce Dr. Keegan. She is the Stephen J. Angelo Professor of Electrical and Systems Engineering, Professor of Material Science Engineering, and Professor of Chemistry at the University of Pennsylvania. She is also Penn Engineering's Associate Dean for Research and the Director of the recently awarded National Science Foundation's Engineering Research Center, or ERC, for the Internet of Things for Precision Agriculture. This is Penn's first ever NSF ERC. It is a flagship program for the Engineering Directorate of the NSF, and it is designed to have engineering systems address societal needs. Dr. Keegan's group is focused on studying nanostructured materials and their integration in electronic, optical, and magnetic devices. Audience, please do type in questions into the Q&A, and at the end of Sherry's talk, we will get to as many as we can by the end of the presentation. Welcome, Dr. Keegan.
Thank you very much. I want to just start by thanking my colleagues, Osek, Leandra, and Diane, for giving me the opportunity today to share some of the recent work in the recently established center. So if you just give me a second, I'm going to share my slides. I have to see a button from the backside. 1 second. Okay. Okay, so hold on, can you see, do you also see you guys? Let me just hide that. So I'm happy today and the opportunity to share with you our recently awarded NSF Engineering Research Center for the Internet of Things for Precision Agriculture, or what we call IoT for Ag for short. And I want to say that I'll introduce you to a real opportunity for us as engineers to think about making societal impact. And so I hope to share with you some of the directions and goals that we have as we've launched this center. And it literally just started 3 weeks ago. The center is a partnership between 3 universities, obviously the University of Pennsylvania as the lead university, Purdue University, the University of California, Merced, and the University of Florida. And as a NSF center, what I'll share with you today was our focus and on making an impact in the area of a need for food, energy, and water security. And we look at how to do that, and I'll share with you our opportunities to look at in bringing together research activities, but it's also a center that brings forth and has sort of equal pillars, not only in research, but in workforce development, which is really our educational program, in creating a diverse group of an involvement of people, whether they're scientists and engineers or more broadly from the public, as well as to create a culture of inclusion amongst the people who are involved in our activities. And in this case too, it's also the National Science Foundation more sort of forward-looking program in its connection to industry. And so a big part of this is also what we call our innovation ecosystem, which brings together with academia, industry, and government partners. So what I'll share with you today too is sort of the story, and it comes from also the need from the National Academy that really said that it was the time for a convergence approach. That term really brings together the ideas, and you'll see this, that we bring together agronomists and agricultural engineers with engineers working on physical systems and cyber-physical systems. And so I'm going to share with you this story in how we look as engineers and scientists to an opportunity to make an impact in food, energy, and water security. Whoops, sorry. So to do that, I just wanted to give you a little bit of background here, that if we think about food, energy, and water security, there's, we look at how we make an impact, and if you look at this problem, the problem really comes from a population that's anticipated to grow to 400 million in the United States and 9.1 billion worldwide of people. There's also a competition for land. There are increased demands for our limited energy and water resources. And as you may know, there's a need for us to develop sustainable processes as we look at agrochemicals, such as fertilizers and other chemicals that are used in farming. And so some of these statistics really come from reports by the United Nations Food and Agricultural Organization, as well as the USDA. And these reports also call for a critical need of increasing food production by 70% and decreasing the use of energy, water, and chemicals by also substantial percentages compared to how they're used today. And so it really sets the stage for what we thought of as a sort of grand challenge, where we think about the opportunity and set the vision for this center that we call IoT for Ag, that we want to ensure food and energy and water security. And of course, as engineers, we want to do that by advancing technology. So our goals are to increase crop production while minimizing the use of energy and water resources and the impact that we have as people in the agricultural practices that it has on the environment. So I had the opportunity about a year ago, almost just a year ago, to visit the National Academy. And I was at a dinner and I looked up, and this is the ceiling from the National Academy, and I took a photo. And if you read along the periphery of the, the circumference, 3 of the phrases read, "To science, pilot of industry, multiplier of the harvest." And we thought that really captured sort of the essence of this center, that we want to bring scientists and engineers together with industry as a way to make an impact, of course, on agriculture. So to do that, we set for ourselves a mission, and our mission is to create and translate to practice Internet of Things technologies for precision agriculture, so that we can, and also to train and educate a diverse workforce that will address the societal grand challenge of food, energy, and water security for decades to come. So today I want to introduce you to what it means. What are Internet of Things technologies that we use often as engineers? It could make an impact in many different domains, from healthcare, for example, to obviously here I'll share with you about agriculture. But the idea is, how do we get more information and more data that allow us to build a picture so that we can make better and more intelligent decisions? And that's really what we want to do in the agricultural environment. And so I'll share with you, this is a schematic where the idea, and you'll see I'll bridge together the idea of bringing physical devices and sensors that we could disperse across agricultural fields that would collect data for things that you can't just see by eye, but that would, for example, would tell you about water, nutrients, ions, pathogens, things that are, we need to understand how they impact crop yield and resilience. We want to be able to transmit that data from the field, either using conventional farming equipment or through robots that are either aerial or ground-based, and that we can keep them monitoring and mapping fields so that they can then share their data to the cloud. And then our data scientists then can build systems that allow farmers to make better decisions, both considering economic decisions, social decisions, in a sort of very broad sense. Apologize, seem to be okay, a little slow. I apologize, I think it's a little slow here. So if we look at it, I just wanted to give you a perspective on the team and thinking about where agricultural crops are in the United States. And so you can see that there's a lot of intensity. Some of these are color-coded, not by intensity, but by each color represents what percentage of the land is devoted to each crop. And it gives you a sense of how important the Eastern Seaboard is, where you'll see, I'll show you some examples in a moment. here in the Midwest, which you certainly will know for its agricultural production, as well as in the West. And so you'll see that our partners really map and represent the diversity of crops that we have across the United States. And currently, US crop production exceeds $140 billion per year. So it's significant. And just to give you a sense of the 4 institutions, you'll see that we're located in many of these agriculturally rich areas. And so you'll see in Purdue, at Penn, University of Florida, and at Merced. And so it gives us as engineers also an opportunity as a way to look at a diversity of crops and also to study the ability for our technologies to make an impact in different agricultural environments, even for the same kind of crop. So why do we look at this now? So you'll see that we look at the opportunity for precision agriculture, and there have been very recent calls that have really called for the importance of this. That's occurred in the United States, where there was a recent report just a few years ago to the president from the Task Force on Agriculture and Rural Prosperity. And if you read this report, one of the key messages is that it is critical that productivity growth not rely on more cultivated land, water, energy, but instead harness the power of innovation and technology. That's largely part because many of these are limited resources. And so it gives us it's really calling for a place where technologies could really make a difference. Another example is from the Future of Food, which is also very recent. It's from the World Bank Group, and it takes a sort of broad look across the world. And the key message there is that digital technologies have the potential to improve efficiency, equity, nutrition and health, and sustainability in the food system. And so we really think that the time is right for us to, as engineers, to be able to make an impact in this area of thinking about food security. So if we ask why, if we look at agriculture today, you might think that the field looks something like this, and we have technologies like tractors, for example. But there are a number of problems that one would recognize. One is that many of the sensor technologies, and I'll show you some examples, are limited into what they can measure, or they're non-existent. Often they're very expensive, which I'll show you in a minute. So you can't actually, it's not affordable for you to put them in different regions of the field to really be able to, map the influence of various targets spatially, temporarily over the time of a growing season, or compositionally in the kinds of targets that you may want to measure. The data that's often, as I mentioned, is usually, maybe I'll show you in a moment, often maybe there's one sensor in a very large field, and so we don't quite get the information that we need. The other thing is that many fields, agricultural fields, are in rural areas, and so the communications infrastructure to actually get data out is typically limited or non-existent. And often what happens is that instead of preventative activities in the farming area, interventions that are made are typically reactive, right? You see that the crop isn't doing well, and then you decide to do something. And typically we then do it in excess. And so this causes an increase in cost, economically in the activities that we make, and then also environmentally in what we introduce to the fields. So an interesting example, this is from a report, a very recent report from Nature, Ecology, and Evolution, where it talks about the influence of pathogens and pests. And they're shown to reduce crop yield by anywhere between 10 to 40%. It does depend on the particular crop, but that's true globally. And it actually shows a very nice map about how influential those are in reducing the yield of crops that one actually gets from farming. And so the question is could we do something? Could we look and be able to probe and measure that there's some infestation or outbreak early before it actually impacts the field and causes a more detrimental impact on the resilience and yield of the crops, as well as, of course, therefore, the cost that is incurred and impact that it has to the farmer. So we'd like to take that farm that I showed you that only had a tractor on it, and then this schematic that I showed you before is really our envision in a schematic way of what we hope the future of farming might look like, where these technologies integrated into agricultural fields would let us change the equation that we have. And so, in fact, in the USDA, a recent USDA report, it was projected that precision agriculture could increase the value of crop production just in the United States by $47 billion per year. And so, as a center, we look to build integrated systems where we bring together all of the kinds of technologies that I show schematically here, in sensors and robots and communications technologies and energy technologies and data science. And what we want to do is build integrated systems that allow us to capture the microclimate and able to us spatially, temporally, and compositionally map, when we say heterogeneous stresses, all of the things that inputs that impact crop yield and resilience. And so our goal is to be able to predict and efficiently control the state of the farm. And we argue what's different now. The term precision agriculture has been around for about 30 years, but the kinds of technologies we have now are really changing the environment and the opportunity. And so we think that the time is right, that the exponential growth in information technology that we all know and appreciate as consumers as well as in data science, and the reduction in the costs of those technologies give an opportunity for us to really make an impact in agricultural practices. And so that's what we aim to do. So I'll just give you a sense. I showed you lots of different kinds of crops, and sort of broadly, we look at the opportunities of being able to test that. So I just show you a couple of examples, which I'll refer to as a center, as part of our lab. And those are just showing an example. This is from the University of Florida. As you can see, this is an orange. It's a little bit early in its growth stage. You can see it still looks a little bit green. But you can see that we have partners where looking at tree crops, looking at row crops. And so we sort of have those as platforms to think about how to develop these kinds of technologies to work in these different agricultural environments. And we bring that up too because these kinds of agricultural crops are in fact the mainstay of our food supply chain. So I have to admit, as an engineer, we take pictures like this that one might think about visually, and we think about how to change that into a diagram. Now, we do bring together in this center a mix of sort of physical engineers or data scientists that think much about wiring diagrams. So as an electrical engineer, I think about wiring diagrams. But my colleagues in agronomy think about the same kind of diagram, but they call it a flow diagram. And what this does is sort of translate this picture into the kinds of activities that we have, which we break into three groups that we call thrusts, that bring together agronomists who really have expertise in understanding plants and soil science, where we look at introducing sensors in that group that can either be on the surface or below the surface of the ground, and robots who can read those technologies. These sensors, by the way, may need communication techniques as well as power. And so we look at how we take sensors, we want to embed them into the agricultural environment. And then from those sensors, we want to read out in something that's referred to as edge communication, sort of far away at a distance, where we can then pick up the information from these sensors using robots that also need to be powered and have communication, and that can then also do some data analysis directly. And that what's known as backhaul communication sends the data from the robot, for example, out to the cloud, where our colleagues in data science can then do data analysis, develop interventions, and make recommendations for decisions that ultimately help the farmer, that feedback in a loop to the activities and influence that they would have on their agricultural crops. So our key is to develop integrated systems for early detection and intervention. So ultimately, altogether, we can improve the outcome in agricultural crop production. So I'll just give you faces. Some of them you'll recognize because they are here at the University of Pennsylvania. Others are not. They're at our partner institutions. But these three thrusts, if you think about it, bring together expertise in what we'll call in agricultural sensor systems. So how do we sense the data? That brings together plant and environmental scientists with folks working on sensors, robots, and robots that can directly map, carry cameras to directly map agricultural fields with the necessary communications that we need out in agricultural fields, and to provide power, for example, for some of the hardware that we showed in this thrust one, as well as to, now that we have the data, how do we respond? And this is where our data sciences with expertise in things like machine learning and sensor fusion, and who can develop controls so that we can provide a decision structure to the farmer so that they can pick and make the right choice for improving the outcomes in their fields. So it brings together a lot of people with different expertise. So I thought I would just give you a sense of some of the problems that we have. When I said, well, we have many targets and many things that ultimately influence the resilience and growth and yield, for example, of plants. So some of those are plant targets, right? To understand how the leaves are growing, what's the status of nutrients, disease, water, for example, pests, and things like that that can be in the soil. How do we also, or on the surface, what's the type, environmental targets, like what's the type of soil, what kind of nutrients are important, is there disease? Also this issue of compaction, of pushing down on the soil over time, and how much water, for example, there is. So there are a lot of, all of these various examples here. We've included a dozen of them, but they can impact crop yield and resilience. And so some of the questions we want to understand is, how do the various abiotic and biotic variables affect crop yield and resilience? And if we develop these technologies, right now we feel that agricultural fields are well undersampled, but ultimately the question is, with what spatial resolution should we deploy technologies? On what timescales, if we think about growing seasons, are as important to capture these variables? And so there's a lot yet to be understood from a perspective of even the agronomy of the plants. We looked at this as an example here. I just showed the same picture here with just some of the kinds of examples of sensors that we want to build to be able to probe some of these targets. And so many of these, as you know, you might be able to image the leaf, right? And I'll show you examples of imaging the leaf or imaging the crops directly using cameras. But many of these you can't actually image directly. And so the question is how do we put sensors on the surface of the ground, in the ground, that will be able to sort of give us that information and get the information out from the field? So this is an example of a conventional water sensor. It's about $1,000 for a single sensor. And so then you look at and you think about, well, where do I place it? Well, usually, farmers will buy one for sort of 100 acres. So they're very expensive, and typically you're not capturing, this is what I mean, in agriculture, they don't really capture the spatial variation across the field. And so our goal is to develop new technologies. You can imagine that places a lot of constraints to be able to put it in an agricultural environment. And so what we're interested in doing is, not that you wouldn't want to calibrate against a sensor that is conventional, but we want to introduce, let's say, unconventional sensors that you could distribute more like seed, that could be put below the surface of the ground or sit on the surface of the ground. And for anyone who knows Penn's campus, the examples of the sensors here are actually fabricated in the Singh Center for Nanotechnology. And the idea behind the sensors is that and this is an example where there's no power that would be required. This is one where you need a little bit of power. But in all of these cases, you could look at building sensors where we target these sensors that were sort of less than a cent to something maybe on the order of $1. And what we rely on is designing devices and using materials that will respond to the target of interest and give us a difference in signal. So for example, the two sensors that I showed you here, in fact, if you were to shine light on this, and you may pick up a little color here, but if you shine light on this sensor, it reflects color, it reflects light, and the color of light that it reflects depends on how much water there is in the environment. And so you can imagine that you could go along an image and just measure for color, and that would give you a way of mapping the distribution of water in the field. Similarly, these sensors are designed to work below the ground. We can't use light, for example, you know that you can't see into the soil. And so we look to radio frequencies, where we look to be able to probe below the surface of the soil, and similarly look at reflected radio waves with a frequency that, again, will depend on the presence of a particular target of interest. If we can do that, the other thing that we have as a part of our sensor, you see here, is that there are a number of robots that are flying. This is an agricultural field. This is in Biglerville, Pennsylvania, just outside. This is work of Dean Kumar in the School of Engineering. And so you can see that these robots are all being deployed, and they can autonomously navigate not only above a canopy of crops, but also in between them, so below that. We also have other ground-based and aerial robots. So there are lots of different capabilities within our center. But the interesting thing here is that if you look, as this robot was flying over, I'll explain that part in a second, it was counting fruit, so that on the fly, these have capabilities to sort of map in the somewhat unstructured environment of the agricultural field. And as they're doing it, they're able to image and sort of count. And this is an example of one from where these robots were deployed to Orange Grove, California, and were counting oranges. And so we think about this, and I think if anyone has even one of these robots that they use and play with at home, you know that of course we need to power them. And so a big part of thinking about how we do this at an agricultural scale is to think about also energy technologies. For example, how do we have robots that don't have to go all the way back to a base station, but could pick up energy that's in the farm? There's actually a fair bit. They can pick up energy from power lines that might be running through the farm. This is supposed to represent an irrigation pivot, right? So there's actually sources of power or other farming equipment from which these robots could power. Or we could think about sharing the area of the field between agriculture and, for example, introducing solar technologies. And so the other thing is that we also are looking at the possibility of developing new battery technologies, and ones which would allow and not wait for a long time when you go to charge them, but would allow very rapid recharging of the batteries that are needed to power the robots. So I mentioned to you that many agricultural fields are in rural areas that have very poor broadband coverage. In fact, our colleagues at Purdue looked at a map, and if you go right down the highway, we have all sorts of cell towers along the highway, and we think we're doing just fine as we drive someplace, as I drove to West Lafayette, Indiana. But as soon as you leave that area, you'll find that there's little to no coverage. And so what we're interested in is developing new capabilities, not just using ones that are, we can sort of pick from that's used for some other reason, but to develop technologies particularly for agricultural use. And so how do we take advantage of getting information and develop communication from sensors to robots or to farming equipment, to developing what's known as millimeter wave technologies, but that are very good at rapid information transfer between, for example, equipment such as the examples here that are shown here. And then also, how do we develop technologies to get it out to the cloud that either can hop through stepping stones or that you have greater range? And so it's sort of a match of often range and rate that we're interested in. But we want to be able to develop these technologies so that we can get information from the various targets that we collect and map in the field. And then we want to be able to overlay the signals. For example, what if we have water and ions? How do we develop an overlay to show where there are correlations, for example, in the field? And so we're also interested in this idea of using this to then fuse the information, or what we call sensor fusion. And then finally, with that data, we want to use things like machine learning, not just to get more data, but how do we get better data so that we can develop models, for example, that are guided by our agronomists that understand the physiology of the plant and the soil, that of course you can get information locally about weather, and also to understand the practices of farmers so that we can develop better models that help us, again, to develop sort of give them a sense of, and in a software sense that you might expect from a tablet, be able to give them information that color codes and lets them know where there's a spot of concern in the field, or what we might joke is a hot spot, but to be able to then have models that we can then indicate and make suggestions. We call them sort of decision agriculture interventions, so that we can take the things that we couldn't see and let them make those interventions earlier. And so that if we can do that in a sort of preventative way, we want to be able to understand the potential of those to improve the outcomes in the field, and that impact also the success economically as well as socially. So I only have a handful of minutes. I just wanted to give you a sense of what our labs look like. Some of these you'll recognize from Penn. Some of these are from our partners, but it's an opportunity where between different universities, we can bring together the skills and the facilities to be able to address this problem. So we really do have agricultural fields, if you're looking at it from a Penn-centric perspective, that are really part of our laboratories. Maybe I'll skip this slide, other than actually, let me tell you that as part of this, we really want to be involved with both, I'll show you in a moment, with industry, but you'll see here we also have we're developing a board, what we call the Ag Systems Advisory Board, but that really represents the end user. So an important part of this problem is not only putting our engineering hats and our scientist hats on, but actually working with industry and government and ultimately the end user of the kinds of technologies. And so what I want to sort of briefly show you is just to give you a sense of some of the other activities. I said there are sort of 4 pillars. I spend a lot of time on the research, but I wanted to share with you the idea that there are lots of activities in workforce development. The idea is to really educate and share the knowledge of these solutions. And I might share with you both what we think of as, who might be involved. And so, so we're very interested in working with students and teachers from K through 12. We have partners from community colleges. Obviously, we have at Penn and our partner universities our undergraduate and graduate students. And then a really unique opportunity to this particular center and the focus that we chose in agriculture is also to make an impact on the education of professionals in agriculture. And so we'll share with you, those can be farmers or growers, but actually they're in the construct of agriculture. There are various extension agents and other professionals in agriculture that are important to sort of translate that technology to. So I'm going to skip the kinds of activities you might expect. That there are all sorts of plans for lectures and hands-on activities and actual work, what are called field days, to work out in the field. And maybe just skip to some of the images that we might have. So there are lots of plans for activities for using robots, teaching about farming. You'll notice locally here in the Morris Arboretum that we have, that's of the University of Pennsylvania. Also a local high school here in Philadelphia that's an urban high school with a 130-acre farm. And so there are activities really meant to bring in and involve lots of people to sort of both share the enthusiasm, but as well as to translate the technologies and a sort of forward-linking a look at where both agriculture and engineering might go. As I mentioned, we also are working with community college, in particular near our partners. This is some of the activities where many of the farmers come for sort of 2-year educational degrees. And so we think about the opportunities to get them involved in activities with the center. That's also something maybe even a little bit unique to agriculture. And of course, our own students. So if there are any of our own students or colleagues on, we look to develop and think about the technologies in the context of the work of the center. And this is an example for professionals. So if you look, there are many professionals. Our partner universities have what they know, for anyone who's not familiar, have what are known as extension facilities, where they really have the mission of not only the science-based solutions that we're talking about, but to make that knowledgeable accessible. And so it's a way to bring people in from the community and to train them to share the kinds of technologies that are being developed, to get their feedback. And so we really view this as a partnership with farmers as well. We also are, in fact, later today, we're very interested in sort of involving a very diverse group. And so we have activities to try and recruit diverse groups to our programs, but more broadly at all of the different educational opportunities that we have in K through 12 through professionals. And so in the interest of time, I won't spend a lot of time on all of these. Also, I'll just show you again, it's the same kind of people that we really want to be able to involve and make a part of the center. And so I'll just give you an example at the university level, also because later today I'll be giving a presentation to the Meyerhoff Scholars, but lots of different student groups that we want to reach out to feel that, that we can involve and bring into the opportunities and sort of, again, share the enthusiasm. And then finally, I wanted to share the importance of innovation here. So of course we have at the University of Pennsylvania, the Penn Center for Innovation, but our partner universities have, let me call it, sister groups as well. And so we're all very interested in thinking about the opportunities that come from the technology. And an important part of this also is really our partnership. And so I'll say that we are very involved. We just established, so we're waiting for people to sign the officials letters. We had a number of 34 different organizations who were involved in supporting the proposal of the center from industry, government, and sort of innovation partners. And so it's very important part for us to have a partnership so that the kinds of technologies that that we would develop would really make an impact, and so that we could translate them from academia out into industry and ultimately to have them in the hands of the people who would use the technology in farmers and growers. And so what I'll do there is sort of wrap up then and just kind of share with you what we look forward to. So this center was funded initially for 5 years, but renewable for another 5. And so we thought about what our goals would be if we looked out in 10 years. And so we want to really build integrated systems from sensors, communications, and responses so that we could at least give it a go at trying to tackle what the UNFAO and the USDA that have expressed as important requirements, as sort of needs in terms of increasing food production and managing our use of energy, water, and chemicals. And so here we look to bring together science and engineering to create these integrated systems. You'll see that as I tried to share with you today that it involves a lot of collaboration through very different disciplines. We want to build that workforce to educate them about the opportunities in agriculture, whether you're an ag person looking at technology or you're a technology person who can now understand the opportunities that are to impact agriculture. And so one of our statements is that we want to have, create more crop for every drop of water or joule of energy, which is one of the units of energy. We want those processes to be sustainable, and ultimately we hope to impact and help to realize this sort of $47 billion per year increase that we hope to achieve in the crop market value in the United States. And so with that, I'll just leave you with this and say that, we will, this was our pitch, we will deliver Internet of Things technologies for precision agriculture that enable food, energy, and water security for the future. So with that, I'll stop and be happy to take any questions.
Wow, thank you, Sherry. That was great to hear your vision for precision agriculture and IoT for AG. We've got a bunch of questions, so let's just kick us off with, I have one question and then 1A. So the first question is, how can we get involved in the center's activities? And the 1A is, what sorts of undergraduate research assistant opportunities are there specifically for Penn CS majors in this area?
Sure, I'd be happy to answer both of those. So we're excited to have people get involved in the center. I said we were just established 3 weeks ago. So we're getting our way there to launch and have all of the people up and ready. So we hope to, our website's under construction, all sorts of things, but we do hope to get lots of people involved, and we'll be sharing that information with the Penn community through websites. For right now, if you want to get involved, you're welcome to email me. We are hiring also an administrative director. I'm happy to say that I think we found the person, but I'll say for now, please email me. We do look, one of the keys is that we really do look at in some of the programs is that we really do want to get undergraduates involved in research. There are examples where we can have, may have support to stay through the summer, to think about how to build on activities and research in this area in senior design projects. And so very much we do encourage, and we'll be looking for opportunities for undergraduate students who are interested in getting involved in research. And so for right now, I'll say reach out to me, tell me where your interests are, and I'll connect you with some of our colleagues who I'm sure will be happy to have you get involved in their work.
Awesome. So I got to ask, what problem are you going to tackle first?
Right. So we looked at in fact, we got asked this question at our, when we were defending this proposal. And we think that the biggest problem we're going to tackle first is water and how to manage water resources. And so it's also from a perspective that from a technology standpoint, it's probably one of the ones that, we think about as being accessible first. And so as a match, there's a, sort of growing consensus that anywhere from the physical devices out to the data science to understand water, that would make a really big impact. So that's where we'll start.
Yeah. Is it possible for you to also collaborate with institutions or individuals outside the US? And a two-part question, do you see opportunities to engage with global organizations with a focus on low-cost IoT technologies for developing communities?
We certainly do. In fact, there is actually an international partnership that is, not only possible, but encouraged. And so we do have some partnerships with folks in South America that we had started with, obviously through the relationships of the faculty, but we are certainly very happy to look to engage at the opportunities. We recognize and that obviously this is a US funded proposal, but we really look at the international opportunities as well. And that is, encouraged as part of our activities. And so we are very happy to engage and to look. In fact, in longer presentations, I would have, shared some of the things that we've been thinking about, and also where, we think about precision agriculture really making a difference outside of the United States too. Even if there's a different economic structure of thinking, how do you structure the kinds of technologies so that, you have a match, right? The socioeconomics aspect of the technologies is also very important.
Good. Another involvement question, how can alumni get involved?
Well, you can also email me, but we'd be very happy to hear about how people are interested in getting involved. Anywhere from, obviously it depends on people's interest and expertise and, what their interest, where they would want to go, but we are very interested in having involvement. That involvement can be anywhere that, maybe it provides guidance, maybe it provides, and that guidance can come in different ways of thinking about how to translate our technologies or what the opportunities are for our technologies, or, someone who has a different problem where they think that the technologies that we're developing may also have applications in agriculture and in other fields. And so we think about that in a very broad sense and are happy for people to share their interests and look at opportunities where, obviously where it makes sense, but where we could, get people involved. So alumni are certainly welcome, and also happy as we develop materials too, and to have opportunities where, again, we get to share the activities of the center and some of the outcomes as we start to have accomplishments with our broader Penn community.
This is great. And it was also really nice to hear right now the sensors are around $1,000 and you're looking at going down to $1 in the cents. How do you roll this integrated approach out widely to get the greatest environmental and sustainable impact? You started to get that towards the end. But.
Right. So one of the things that we really looked at is that in order for us to look at and have this be economical, I'll tell you, by the way, we also have an economist as a part of our, an agricultural economist as a part of our team. So it's very important for us to understand that we look at technologies that are, that can be practical, frankly, even from an economic standpoint. And so that's where we looked at really not $1,000, but thinking about $1, even things that are less than a cent. So it depends on the different kinds of sensors and where we may deploy them. And that's really where we have to understand how we want to deploy them, how many we want to deploy, how often do we need to, when in the season. And so we have to understand those problems. But we do think about, manufacturing processes that would let us, realize those targets. And we also are, as I mentioned, a big part of this is working with and getting the guidance of industry. And so I'll say that until they sign their names and tell me that I can freely share their names with the broader public, but I'll just tell you that, well, you'll find that we've been speaking to people you'll recognize from agriculture, big and small companies as well as conventional technology companies that you might not have thought would be involved in agriculture, but actually because of the technology side and the bringing of those two together, there's a mix of the different environments. And we hope to support that as well, even as a platform for communication as coming through the center.
That's great. Going back to the diversity, do you have examples of how you have or plan to involve diverse folks from the local community?
Yeah, so we look to involve diverse folks through, I'll say that formally the center started 3 weeks ago, so we're just starting. But I think that you'll find that the faculty here and the students have been very involved in working with students from the community, and we have ideas about programs where we want to continue that. So for example, we have opportunities where we look to go and have a partner in the high schools here in Philadelphia. One of those is in fact an agricultural high school, as I mentioned, in the Saul High School. And so we look to, in fact, that is a formal partnership with the Sun Agreement in between, but where we will look to share the educationally the materials and also to bring and involve students from the high school in research. That's one example. We also have K through 12 activities that we will also be involved in. And so we think about, I guess those are two of the examples that I would say would be local to Philadelphia. But, in different matches and different degrees, we hope to bring people to this university.
Great. Well, Sherry, do you have any closing remarks before we hand it over to OSEC to close the presentation?
No, I just welcome everybody's interest and involvement. And so, please reach out, and I promise we'll be reaching out to the Penn community and sharing with you the opportunities and activities of the new IoT for Ag Center.
This has been very exciting to hear all of these plans. I know this has been a long time in the making, so thank you for sharing. OSEC, do you want to close us off here?
Yes, let me just join you in thanking Sherry for this fantastic presentation. I think it's, the future looks brighter. We have over 7 billion people on the planet, and each of these individuals have to be fed. And so the research that you're doing has very practical value in the real world. So I appreciate you sharing your research with us. And hopefully the constituents, and I'm glad you have diversity included in this program. Because if you look at people that live in the city, there are really no urban farms. And so children go around without seeing what a farm actually looks like. But by including them in this program, they'll have an opportunity to learn more about farming, and especially using technology as part of that process. And of course, it's just the language, precision agriculture is fantastic. When you say precision agriculture, it means that it is very, very well focused, and of course has the power to transform how people plant, not just here in the United States, but around the world. So I'm quite pleased that you have an international component to it, because the majority of the people that benefit from this, if it's done globally, live outside of the United States, particularly in the global South. And of course, this is all part of a way that we can fight climate change and global warming and increase food productivity overall for people to have. So thank you very much, Professor Keegan. Thank you, Leandra, for moderating. You did a fantastic job. And Diane is always behind us, taking care of the technical stuff. So thank you, Diane. And I would like to invite our audience to join us tomorrow, day 3 of Climate Week at Penn, where we'll be discussing carbon offsets. It's a fantastic panel of Penn and outside industry people that will discuss this issue and as it relates to all of us, particularly folks that live in West Philadelphia. So with that, and all of us here at Penn Engineering, I want to thank you for participating. Thank you to Sherry, Leandra, Diane, and we'll see you tomorrow at 11 a.m. Thank you.